Dark matter's secret force does the opposite of what scientists expected. If you like my videos, subscribe my channel and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. For discussion, write down your views in comments. For decades, scientists have imagined dark matter as the invisible scaffolding of the universe, an elusive substance that does not emit or absorb light, yet exerts gravity strongly enough to shape galaxies and enormous cosmic structures. But what if dark matter's not as simple as we thought? What if its particles can interact with one another through a completely hidden force that ordinary matter cannot detect? A new theoretical study suggests exactly that possibility, and the result is surprisingly counterintuitive. You might expect an additional attractive force between dark matter particles to make galaxies and cosmic structures grow faster. Instead, researchers find that this hidden force can actually slow the growth of the universe's largest structures. The reason is an unexpected side effect. As the universe expands, the dark matter particles can effectively become lighter, weakening their gravitational influence and partially, or in many cases substantially, offsetting the additional attraction. To understand why scientists are considering such an unusual idea, we first need to look at what we actually know about dark matter. The strange substance has never been directly observed through light. Everything we know about it has largely come from its gravitational effects. We see galaxies rotating faster than the visible matter inside them should allow, and we observe enormous structures whose behavior suggests that far more mass exists than telescopes can see. Dark matter appears to provide that missing gravitational influence, but gravity may not be the whole story. Researchers are increasingly asking whether dark matter particles could have their own interactions, forces that operate almost entirely within the dark sector and leave ordinary matter largely unaffected. Scientists call this possibility a dark force. Why would anyone introduce an entirely new force into cosmology? One reason is that increasingly precise observations have revealed small tensions between different measurements of the universe. Observations of cosmic expansion and the development of galaxies and large-scale structures do not always fit together perfectly within the simplest version of the standard cosmological model. Some measurements of the distant universe suggest that cosmic expansion may have been somewhat slower in the past than standard predictions indicate. Meanwhile, observations of the cosmic microwave background have provided evidence about how matter was distributed in the early universe, and some measurements suggest differences in how strongly matter appears to be clustered today. These discrepancies are relatively small, and they do not prove that the standard model is wrong, but they are interesting enough to motivate scientists to investigate whether something important could be missing. One possibility is an additional long-range attractive force acting between dark matter particles. Imagine two dark matter particles that already attract one another gravitationally. Now imagine they also experience another force pulling them together. At first glance, the consequences seem obvious. The particles should gather more efficiently, clumps of dark matter should become denser and galaxies, and larger structures should form more rapidly. In fact, this is one of the reasons such a force might initially seem attractive as a possible explanation for certain observations. But the researchers discovered that the story does not end with stronger attraction. The hidden interaction can change another fundamental property of dark matter as the universe expands. In the theoretical models studied by the researchers, dark matter particles can effectively lose mass over cosmic time. That is crucial because mass determines how strongly matter contributes to gravitational structure formation. Wow. So while the additional force pulls dark matter particles together more strongly, the particles' decreasing effective mass weakens the gravitational influence they exert on the surrounding universe. The two effects compete with each other. The hidden force tries to increase clustering, while the reduction in effective mass suppresses the gravitational impact of that clustering. The result is one of the strangest aspects of the new research. More attraction does not necessarily mean faster cosmic growth. In many of the models examined, the additional force actually leads to a suppression of the growth of large-scale cosmic structures. Dark matter can become more tightly clustered while simultaneously producing a weaker overall gravitational imprint than you might expect. It is a perfect example of how intuitive reasoning can fail when several interconnected physical effects operate at cosmological scales. This finding could become especially important when scientists develop more complicated models involving dark matter and dark energy. Recent observations from instruments such as the Dark Energy Spectroscopic Instrument, or DESI, have encouraged researchers to investigate possibilities beyond the simplest picture of cosmic evolution. Some theoretical models proposed to explain these observations involve interactions within the dark sector. The new study suggests that if dark matter particles experience an additional attractive force, scientists cannot simply calculate the stronger attraction and assume that structure formation will accelerate. They also need to account for the possibility that the dark matter becomes effectively lighter as the universe evolves. That could provide an important new constraint on theories of hidden dark sector physics. If future observations reveal how rapidly galaxies and larger structures form throughout cosmic history, scientists may be able to compare those measurements with predictions from different dark force models. The next generation of astronomical surveys could therefore help determine whether dark matter is truly interacting through an unseen force, or whether the apparent cosmic tensions have another explanation entirely. But it is important to emphasize what this study does not prove. Scientists have not discovered a dark force experimentally, and they have not directly detected dark matter particles interacting with one another. This is theoretical research exploring what the consequences would be if such an interaction existed. The study shows that an attractive dark force produces a much more complicated outcome than simple intuition would suggest. And that may be the most fascinating lesson of all. The universe repeatedly reminds us that seemingly straightforward physical ideas can produce unexpected consequences when viewed on the largest scales. A force that pulls dark matter together sounds like something that should accelerate the growth of galaxies. Yet under these models, that same interaction can make dark matter effectively lighter and ultimately suppress the growth of cosmic structure. Dark matter remains one of the greatest mysteries in modern physics. We know its gravitational influence is there, but we still do not know exactly what it is made of, or whether gravity is the only force acting upon it. If future observations reveal evidence of interactions within the dark sector, we may discover that the invisible universe is far more complicated than we ever imagined. And ironically, the force hiding in the darkness may not make the universe grow faster after all. It may be doing the exact opposite.